Hi everyone, in this video we're looking at how graphs of functions relate to their derivatives, and so we're going to look at some of these on a graphing program, not that one by the way, this one here. So first of all, looking at a straight line, so hopefully you can see up here I've got y equals ax plus b, so a being the gradient and b being the y-intercept. So when I change b, my graph moves up or down accordingly. And when I change a, my gradient changes accordingly as well. But you'll just notice underneath here that I've got d by dx of ax plus b. And what that's giving me is the derivative of my function. And hopefully you notice that as I change the gradient, my derivative changes as well. And in fact, my derivative is precisely equal to my gradient. And that actually makes sense because the derivative of a function is the gradient of that function. So that's what's happening for a straight line. Let's look at a quadratic. So with a quadratic, we've got ax squared plus bx plus c. And unsurprisingly, as I change c, my quadratic graph moves up and down. And as I change b, it moves it because that's affecting its intercept, so it's moving it from left to right. And then as I change a, that's affecting the slimness or the thickness of my parabola. Okay, and you'll notice that there's that yellow line there as well, and that yellow line is the derivative of the function. And so if we look at the things that affect that line, if we look at b moves the line but doesn't actually change the gradient of the line, and c has no effect on the line whatsoever because it's only moving it up or down, it's not affecting the gradient. But a changes the gradient of that line, and that's because a is the coefficient of the x squared term, and so when we differentiate that, it's affecting the gradient of the derivative that we get, which is a line. So I guess in summary is when you are differentiating a quadratic, your result is that yellow line. So you get a straight line representing the gradient of a quadratic. Finally, let's look at a cubic. So a cubic being something with a power of 3 in it. And the cubic on this graph is the red graph. And I can change all my variables. If I change a from positive to negative, it changes it from being going up from the left or coming down from the left, depending on whether it's positive or negative. And you know, b shifts it around as well, and c and d do things to it as well. But the point that I'm trying to make is that the derivative of a cubic is going to be a parabola, and so that's where this black curve here comes in. That's the parabola, and that parabola represents the gradient of our cubic. So you'll notice, I might just try and make this a little bit wider to illustrate what I'm looking for. So you'll notice that up this top point here we have a gradient of 0, and at the same x coordinate our parabola goes through the x-axis at 0 on the y-axis. So our intercepts of our quadratic correspond to our maximum and minimum turning points on our cubic, and where our parabola has a turning point, that's equal to the point of inflection where our graph changes from having a gradient that's decreasing to starting to increase again. So in summary, when we've got a straight line, the derivative of a straight line is simply a number. The derivative of a quadratic, and I've somehow lost my quadratic here, the derivative of a quadratic is a straight line, and the derivative of a cubic is a parabola. And that's in essence what you need to know to do this next exercise, which is 22.03. But we'll probably also talk about this in class a bit. Thank you.